Welcome, guys. In this video, we are going to study one of the very powerful techniques of integration known as integration by substitution. This technique has its roots in chain rule. Let's recall chain rule first. Let's assume that big F here is antiderivative of small function f of x. Then, according to chain rule, if we are taking derivative of f at g of x, it is equal to moving out from outer functions towards the inner ones. First, we take derivative of big F at g of x, then we take derivative of inner function. We are taking derivative of g of x, so here we have g prime of x. Now let's rewrite this equation in integral form. Let's start by writing down the right side. So we'll have integral of big F prime at g of x multiplied by g prime of x dx is equal to antiderivative of f at g of x plus constant c. Now, since big F is antiderivative of f of x, we can further simplify it into the following form. Small f at g of x, g prime of x dx is equal to big F at g of x plus constant of integration. Now, here is our step where we introduce substitution. Let's substitute u instead of function g of x. If we take derivative of du, if we take derivative of u base dx, it is equal to g prime of x. Rewriting this equation in integral form. In differential form, we'll have du equal to g prime of x multiplied by dx. Okay, now this equation here will be transformed into the following one. We'll have integral f, instead of g of x, we have u. Instead of g of x here, we'll have u, and instead of g prime x dx, we'll substitute du. Then this equation here is transformed into f at u du equal to f at u, antiderivative of f at u plus constant of integration. So this technique here allows us to solve the following integral by introducing substitution u and transforming into the following form. Now let's take a look at a couple of examples. In our previous example, we were able to recognize composition of functions f of g of x right away, and our substitution was obvious. If that's not the case, the method may still apply, but you'll have to apply a bit more work. In this case, looking at this integral here, the first thing that might come to our mind is that we need to try to replace x minus 1 with u. So let's try that. Let's call x minus 1 as u. Then dx or du is equal to dx. But we have a problem right now. We need to also replace x squared here. We can still do that by representing x as u plus 1, and x squared is equal to u squared plus 2u plus 1. All right, so our integral is then transformed into the following form. We'll have integral of u squared plus 2u plus 1 multiplied by square root of u, and dx it will be replaced by du. All right, now let's try to write this into the following form by opening the brackets. We'll have u to the power of 2.5 plus 2u to the power of 1.5 plus u to the power of 0.5. All right, now using properties of indefinite integrals, we can take integrals of each term here separately. So we'll have u to the power of 3.5 divided by 3.5 plus 2u to the power of 2.5 divided by 2.5 plus u to the power of 1.5 divided by 1.5 and plus constant of integration. Now we are going to substitute x minus 1 instead of u back, and substituting x minus 1 instead of u's will get our final integral as a function of x. All right, now let's take a look at one more example. Now let's try to solve the following integral. It might come to our mind that we should use the following u substitution right away. We should try 2 minus x squared, but this substitution here will not work since u is equal to minus 2x dx, and this term minus x is left hanging since it doesn't appear in our original integral over there. So we are not doing this substitution, but we are looking at this integral here, and it resembles as the following integral. Integral of trigonometric function. Let's try taking derivative of arcsine of x. Derivative of arcsine of x dx is equal to 1 over 1 minus x squared. Now this integral is similar to a derivative of arcsine, so we'll try to bring this into this form over here. Let's try to factor out 2 out of square root here. So we'll have 1 minus x squared over 2 root of 2. Then if we multiply those two, we'll get the same expression. Okay, now if we to make it more clear, let's bring this constant out of integral sign. We'll have dx over root of 1 minus x squared over 2. Now it resembles as the derivative of arcsine even more. However, here we have x squared, and in this case we have x squared over 2. Then applying the following substitution will do the trick. If we use u is equal to x over root of 2, then u squared will be equal to x squared over 2, exactly what we need. Taking derivative of du will be, it is equal to 1 over square root of 2 dx. So we have no problem with that, since we can always artificially multiply and divide by some constant. So our integral here is transformed into, instead of dx, we'll have a root of 2 du. So root of 2's will cancel out. We'll have integral of du over square root of 1 minus x squared over 2 is then replaced by u squared. All right, perfect. Now here, this is this here is an integral of arcsine of u plus constant of integration. And substituting our u back, we'll get arcsine of x over square root of 2 plus constant. All right, guys, now if you see an integral like in our previous example, which resembles u derivative of one of the inverse trigonometric functions, then in our book we have the following formulas that generalize cases like this. You can memorize these formulas, and when you see an integral of this form next time, then you don't have to do all of the steps, and you will know the answer right away. But you don't have to memorize it, since if you can recognize this form that it is a derivative of trigonometric function, inverse trigonometric function, then that's enough. Just use the U substitution, and you will get to these formulas anyway. In general, the method of U substitution mainly requires practice, and as you can see, it's mainly a guesswork. Now this will conclude our video on method of U substitution. Thank you for watching, guys.